In this video, we're going to start Chapter 3 of the algebra textbook. Chapter 3, you can see, is on polynomial and rational functions. In this video, we're going to go through the opening section, which is on quadratic functions. So in Chapter 2, we studied in detail two different equation types in two variables and their corresponding graphs in the Cartesian plane. We studied the equations and graphs of circles, as well as the equations and graphs of lines. Okay, but with lines, we were actually able to make the linear function as well. We weren't able to do this with circles. No circle is going to be a function, but the vast majority of lines that you can draw in the Cartesian plane are going to be functions. So with that, we created the linear function, which corresponds to the graph of any line you could possibly draw in the Cartesian plane except for a vertical line, which makes sense because a vertical line isn't a function. So what we're going to do now in Chapter 3 and Chapter 4 is we're going to study more function types and their corresponding graphs. Now, but when it comes to more types of relations, like circles, we're going to study more equations like this and the corresponding graphs in Chapter 7. But right now, in these upcoming chapters, we're going to study different function types. And we're going to start with polynomial functions. Now, as we know, though, a linear expression is a subset of polynomial expressions. So technically, the linear function is a polynomial function, technically. The function expression is a linear expression. Every single term has an x variable raised to a whole number power, so it's polynomial. But in this case, the highest degree term is 1. We have an x to the first term here and an x to the 0 term here, a constant. So this is linear. But we put this type of function into its own category, separate from just a general polynomial function, because it has its own unique graph, the line. And similarly, we're going to do the same thing with quadratic functions. The quadratic function is going to have its own unique graph type. But then from there, when you get to polynomials of degree higher than 2, any degree higher than 2 polynomial function is going to have a similar enough graph to where all of those just get grouped together into one function type. So if the linear function, we can think about in general, so with a function, you're going to have the function equation, you're going to have the output variable isolated by itself on one side with the expression of the input, just the input variables on the other side. So what we can see here is that the linear function is, here's the output variable, the linear function in just a single variable input, in general is just a ax plus b, right? That's a general linear expression. But this happens to correspond to the slope-intercept form, to where the constant a is the slope of the line and the constant b is the y-intercept. But this is a general form of a linear function. So if we're going to extend this to quadratic, then what we're going to do is, so we've got the output variable isolated on one side, and now let's just write out a general quadratic expression in x. Well, we know a quadratic expression is just, it's a polynomial expression where every single term is going to have degree 2 or lower, with at least one term being degree 2, or it would be linear. So with that, we can say that in general, a quadratic function is going to be of the form a constant times x squared plus a constant times x, because we can have linear terms, it's degree 2 or lower, plus just a constant, that's an x to the 0, where just a can't be 0 or else it's linear. But b and c can be any number, doesn't matter. Okay, and so with that, if we come to the start of this section, that's exactly what we see. So it says in Chapter 2, we defined a function of the form, this linear function here. So now if this is a linear expression here, if we extend this to the idea of a quadratic function, we're going to write a general quadratic expression. And that's the general form of the quadratic function. Okay, and so the unique graph type that's associated with a quadratic function, if you plot this in the xy plane, so with x on the horizontal axis and then the y or the f of x on the vertical axis, the result is you're going to get a parabola. In all cases, no matter what coefficients you use for a, b, and c, the graph of any quadratic function is going to be a parabola, which looks like this. But it can be located at different points in the plane. It can have like different amounts of wideness or steepness. It could also be pointing downward. But in general, again, every quadratic function, if you graph it, is going to have the shape of a parabola like this. Now, if you think back to the linear equations and linear functions section, we started off by looking at a more general form of a linear equation in two variables. And this was representative of any line in any orientation in the Cartesian plane, including vertical lines, which is why we technically didn't refer to this as a function. We separately developed the linear function, which corresponds to any line in any orientation in the Cartesian plane except for vertical lines, which makes sense because any non-vertical line is going to pass the vertical line test. It's going to be a function. But here, in this section, we started from the very beginning with the quadratic function, just y by itself on one side and a quadratic expression in one variable, x. But what about a more general form of a quadratic? So, okay, if we do the same idea as, so the most general form of a linear equation in two variables, x and y, linear is just, so a times x plus b times y, and then we can say plus a constant is equal to 0. Okay, now, but if we apply this same idea for a completely general quadratic equation in two variables, x and y, then the idea is every single term is degree 2 or lower. It's going to be a polynomial equation where every single term is of degree 2 or lower. So in complete general, this would be ax squared, there's a quadratic term, plus by squared, there's another quadratic term, plus cxy, that's a quadratic term because the total degree is 2. Okay, so there's all the possible quadratic terms in x and y, but we can also have linear terms, so plus dx plus ey. Okay, there's all the possible linear terms. Now we can have a constant term is equal to 0. Okay, so yeah, there you go. There would be a general form of a quadratic equation in two variables. This is the parallel to the linear equation in two variables in complete general. The form we were given was like this, but we can bring the c to the left side. The sign, it's an arbitrary constant, so we'll just put the sign of the c as positive. So this would be the parallel to the general linear equation in two variables. So if it's going to follow a similar pattern to what we saw with the linear equation and the linear function, then you would think that if we plotted any equation like this, that has a form like this in the xy plane, we would get parabolas, just like we got lines with the linear equation in two variables. Well, because of the increased complexity of the equation going from linear to quadratic, it actually doesn't work out this way. For example, if we write the general form for the equation of a circle, this is quadratic. In this case, a is equal to 1, b is equal to 1, c is equal to 0, and then you just include these last three terms. So a circle is quadratic in x and y, and a circle is certainly not a parabola. And we're going to see in chapter 7 that the ellipse is quadratic, the hyperbola is quadratic. So this is different from what we saw with the linear equation in linear function, in that the quadratic function is in its own separate, unique category in relation to the graph it's associated with. Okay, now we can also think about how this function, so this is a function, can be extended to more than two variables or more than one input variable, in a similar way to how we thought about linear equations are extended to more than two variables, or even the equation of a circle. And what we saw was that if we had a linear equation in three variables and we plotted this in the 3D Cartesian coordinate system, the result is a plane, not a line. And if in a similar way, if we extended the equation of a circle to three variables and plotted this in the 3D Cartesian coordinate system, the result would be a sphere with radius r centered at HKL, not a circle. And the result would be similar if we extended this to a quadratic function with two variable inputs. So a general quadratic expression in x and y would be, once again, okay, if we plotted this in the 3D Cartesian coordinate system, it's not going to be a parabola. Now, what exactly this graph would look like, and as well as equations of planes and other functions and expressions in 3D space, that's something we study at the beginning of Calculus 3. Okay, now, but as we've been talking about, we study functions and equations in 2D and 3D. We can visualize these graphs in 3D, but we can still abstractly extend these concepts past 3D. And it should be no problem for you to understand how to extend an expression past just two variables. For example, if we wanted to write a quadratic function with three variable inputs, well, you understand the definition of a quadratic expression. And so a quadratic expression in three variables, it's just that the degree of each term is just a polynomial expression where the degree of each term is of 2 or lower. So in three variables, what are all of the possible terms, quadratic terms we can have? So, okay, well, we can have an x squared term with any constant out front. Y squared term, that's quadratic. A z squared term. Okay, an xy term, that's quadratic. A yz term. A xz term. Okay, that's all the possible quadratic terms in relation to three variables. So now, but we can also have linear terms. Okay, and now we can have a constant. So that would be the general form of a quadratic function with three variable inputs. Okay, but now let's come back to the quadratic function with one variable input, or the quadratic function in two variables. One output and one input. So again, the graph of any quadratic function, you graph the f of x or the y on the output, the vertical axis, and then the x on the horizontal input axis in the Cartesian plane. The graph of any function with this form is going to be a parabola. Okay, a parabola like shown here. The parabola is either going to be facing upward like this or facing downward like this. It's never going to be slanted. It's going to be either facing upward or downward. And it can be located anywhere in the plane. And the way you think about where it's located is where its vertex is. So this vertex point, which you can think about is if the parabola is facing upward, it's the lowest point on the parabola in terms of the output, the y value. If the parabola is facing downward, it's the maximum point. But the parabola can be located anywhere in the plane in terms of its vertex. And then from there, just based on the different constants, it can have just different levels of how narrow it is or how wide it is. But it's always going to be this symmetric shape here that's pointing upward or downward. And it's because it's symmetric, another characteristic of a parabola is that it has this axis of symmetry with the equation x is equal to the x coordinate of the vertex. Okay, and so what we can do is, this is the general form for a parabola. But as we know, we can take these equations and put them into more descriptive form, where we can read off features of the associated graph of that function or equation directly from the equation. Well, we can do the same thing here with the quadratic function. We can put this into what's called vertex form, where in vertex form, what you have is, you have this equation. We can convert this into this, and we'll talk about how to do that in a second. But in this form, what you can read off is that the vertex is located at HK. So the vertex is at HK. Okay, you can also, if A is positive, it's an upward-facing parabola. If A is negative, it's a downward-facing parabola. And then furthermore, since we have the vertex coordinates, then we know that the equation of the vertical line for the axis of symmetry, it's going to be x is equal to h. So with this form here, we've got all of the information we need about the graph of this function, the corresponding parabola. And that's exactly what they outline here. They talk about the vertex form and everything all the information we can get about the graph from the vertex form. The vertex at h comma k, whether or not it's upward facing or downward facing, and the equation for the axis of symmetry. Oh yeah, now they also mention how we can note that the maximum point, in terms of the maximum value of the function, if it's a downward facing parabola, that's going to be the vertex value, the vertex y coordinate. If it's upward facing, then the minimum value of the function is going to be at the y coordinate of the vertex. So with the vertex coordinate, we have the maximum or minimum value of the function. So with that, we can easily write the range of the quadratic function. So yeah, in regards to domain and range, well, we've got this is a polynomial. You can input anything you want into a polynomial. There's no dividing by zero. There's no negatives under even root radicals, anything like that. You can input anything you want into a polynomial. So the domain of any quadratic function is going to be negative infinity to infinity. And then the range is going to be, if it's an upward-facing parabola, then it's going to be, the minimum is going to be the y-coordinate of the vertex, but it includes that, to infinity. If it's a downward-facing parabola, the range is going to be negative infinity to the y-coordinate of the vertex. Okay, so we can work an example problem here. We've got this function. We can see this is a quadratic function in vertex form. Okay, the first question is this facing upward or downward? It's facing downward. This is negative. What's the vertex? H, comma, K. And whenever you're reading off the vertex, you need to remember what the vertex form is. It has a minus in front of the h and a plus in front of the k. So since this is -1, then the vertex is at the x coordinate is +1. Since this is +8, the vertex y coordinate is at +8. Okay, what about the x-intercepts? Well, we just set the function equal to 0 and solve for x. We can have more than one x-intercept. Subtract both sides by 8. Divide both sides by -2. Take the square root of both sides. So x is equal to 1 plus or minus 2. So x is equal to 3 and x is equal to -1. Those are the two x-intercepts. What about the y-intercepts? Well, with a function, there's going to be one y-intercept or no y-intercepts. And we know that's just when x is equal to 0, so we just evaluate the function at 0. So we get -1 squared is 1, so -2 plus 8, 6. Okay, so now sketch the function. Well, okay, that's going to be, we have a lot of information now to do this. Okay, so the x-intercepts are at -1 and 3. The vertex is at 1, 8, so 1, 1, 2, 3, 4, 5, and then we'll have like 6, 7, 8. So axis of symmetry is going to go through here. Okay, we also have the y-intercept at 1, 2, 3, 4, 5, 6. So that's now a good amount of information to sketch this. There we go. Axis of symmetry is at x is equal to 1. Maximum value is at y is equal to 8. Domain of any parabola is -infinity to infinity. The range is going to be -infinity to 8, including 8. Okay. Now, next, what we want to look at is if we start with this general form here for a quadratic function, how can we put this into the vertex form? Well, we can use completing the square to do this in the same way that we used completing the square to go from the general form for the equation of a circle to the standard form. Okay, so if we look at this example here, so we've got f of x okay, and so if we're trying to get to a form that's like this, then what we need to do is we need to add something to these two terms to create a perfect square trinomial. And then that will allow us to get a term like this, x minus some constant squared. So what we want to do is, so to do the perfect square trinomial, we need to have a coefficient of 1 in front of the x squared term. So we can factor out a 3 here, and we get x squared plus 4x. Okay, and now leave a space here, and then plus 5. Okay, so now let's create a perfect square trinomial, x squared plus 4x, and let's add something here to create the perfect square trinomial. So you have x plus a squared is x squared plus 2ax plus a squared. So in this case, 2a is equal to 4, a is equal to 2. So a squared is 4. So now we've got a perfect square trinomial, but we don't want to change this expression, so we need to subtract something over here. And that's going to be 12. This is a little bit confusing because we've had to factor out this 3, but the idea is we'd add a 12 here and then subtract a 12 over here. And then so this 3x squared plus 12x plus 12, we factor out a 3. We get x squared plus 4x plus 4. But then since we subtracted this 12 here, we didn't change the expression. So the result is we've got, so we can now turn this into x plus 2 squared. And then over here we've got 5 minus 12 is minus 7, and there we go. Now we can read off. The center is at, or the vertex is at minus 2, 7. It's upward facing. Axis of symmetry at x is equal to minus 2. We get the y-intercept, the x-intercepts, just by setting this equal to 0, solving for x, or evaluating f of 0. Okay? Now the next thing they do is they create the vertex formula. And all the vertex formula is that you can start with this general form here for a quadratic function. And what they're wanting to do is allow you to just use these coefficients and plug them into a formula to get the vertex coordinates. And so they do this by they complete the square with this general form. They go through the whole process, and when you do this, you get this is what you get. Okay, and so what you can see is that h is equal to minus b over 2a, and k is equal to 4ac minus b squared over 4a. But what they do is that they say that the official vertex formula is that if you have a parabola with the general form like this, then they say that the vertex is located at minus b over 2a, and then instead of having to memorize what k is, they just say it's at f of minus b over 2a. Right? You just plug the x coordinate into the function. So if we look here, for example, if you've got the parabola or the quadratic function minus x squared plus 4x minus 5, well, okay, where's the vertex located? So you've got, it's okay, minus b over 2 times minus 1, so minus 4 over minus 2, that's positive 2. Okay, now the y coordinate is just plug in f of 2, or plug in x is equal to 2 into the function. So that's going to be minus 4 plus 8 minus 5. So 4 minus 5 minus 1. There you go. Okay, now next it says the x-intercepts of a quadratic function, and here they give the general form here. Well, what are the x-intercepts? It's you set the f of x equal to 0, and you're solving this quadratic equation is what you're doing, right? You're solving ax squared plus bx plus c is equal to 0. Okay, and so in general, it's the x-intercepts it's the quadratic formula, right? And so we can analyze the x-intercepts of a parabola from the perspective of the quadratic formula, and I mean specifically the discriminant, right? Remember, the discriminant, it gives you information about, if you just analyze, okay, if you start here and you say, okay, what is b squared minus 4ac? That's going to tell you if this is positive, there's two real solutions. If this is 0, there's one real solution. If this is negative, there's no real solutions. Now, when it comes to the actual parabola, the graph of this graph, remember, in this course, we only work with graphs of equations and functions that in terms of real numbers. We don't plot imaginary numbers associated with equations until a later course. So what you can think about is that if the discriminant is positive, then it's going to be a parabola that crosses the x-axis twice, like this. If the discriminant is 0, then it's going to just, the vertex is going to touch the x-axis. It's going to have one x-intercept. Okay, if the discriminant is negative, then it's not going to touch the x-axis. So that's interesting. Now, but you can also notice that there's always going to be a y-intercept no matter what for the quadratic function. Okay, now, applications involving quadratic functions. Quadratic functions can be used in a variety of applications in which a variable is optimized. That is, the vertex of a parabola gives the maximum or minimum value of the dependent variable. We show 3 such applications in the next 3 examples. So, a stone is thrown from a 100-meter cliff at an initial speed of 20 meters per second at an angle of 30 degrees from the horizontal. The height of the stone can be modeled by this quadratic function with input time, where h of t is the height in meters and t is the time in seconds after the stone is released. So what we're going to see is that projectile motion, which is it's something is thrown and there's no engine on it propelling it. It's just under the natural influence of gravity, is going to, the path of motion is going to be parabolic. When we get to calculus and we're combining calculus with physics, we'll see where this comes from. Again, if you've got something that's in flight under the pure influence of gravity, there's no motor on it, then its path of travel is going to be parabolic. Yes, if there's wind resistance, then that would alter things a little bit, but fundamentally it's parabolic. If you add in wind resistance, then it's going to be just a deviation from a parabolic path. So, okay, if we're going to analyze this quadratic function here from the perspective of this real-life application, so determine the time at which the stone will be at its maximum height. So what they're saying is the stone is thrown, here's this cliff, the stone is thrown at 30 degrees. So it's going to take this parabolic path. Well, what's the maximum height? Well, we find the vertex of the parabola, right? Use the vertex formula. It's a downward-facing parabola. Use the vertex formula. Well, okay, no, it wants the time at which the stone will be at its maximum height. So that would be the vertex formula and get the x-coordinate of the vertex, or the t-coordinate. And the maximum height would be you just evaluate the function at that time. And now the time at which the stone will hit the ground would be, well, you know that it's going to be when h is equal to 0, right? Because they're saying the coordinate system here is based on at ground level being 0. So you start, the initial height is 100. So you just need to solve for when h is equal to 0. Solve for t. And they do that, and they get 2 values. If you come here, they get 2 values for t. Okay, but since one of the answers is that t is negative, and that doesn't make sense in this case. So we just take when we know that what we're looking for is this time here. That's the time when the stone hits the ground. And you might think, well, wait a minute, why did this happen? I mean, did the math break? Well, no, in actuality, we could have started a problem like this and specified the domain of the function. And that, okay, when you start off with this model, you say, look, t is greater than 0. That's part of the domain. There's no time negative, so we're not considering negative time. So in that case, you'd look here and say, okay, well, this is outside of the domain of the function. Okay, let's see. This example, it says a parking area is to be constructed adjacent to a road. The developer has purchased 340 feet of fencing. Determine dimensions for the parking lot that would maximize the area. Then find the maximum area. So, okay, we've got, let's see. So the fencing is, the total perimeter is x plus y is equal to 340. So 2x plus y is equal to 340. Okay, now the area is equal to x times y, but we can see that if we solve for with this constraint here, we can get the area as a function of one variable, let's say x, and we can write this as, so we can see y is equal to 340 minus 2x. Because we have this constraint here, and it's rectangular, we know it's rectangular, and we've got this total amount of fencing, we're able to turn this into to get the area of the parking lot as a function of just one of the dimensions of the rectangle. So what we get is that a of x is equal to 340x minus 2x squared. So let's put that into, okay, and there we go. That's a quadratic function, right? We've got with a is equal to minus 2, b is equal to 340, and c is equal to 0. So if we're trying to maximize the area, well, okay, this is going to be a downward-facing parabola, right? So we're looking for that, this value here, but then we're also going to look for what the x dimension needs to be, so we build the parking lot correctly. And so you just analyze it, right? Use the vertex formula or complete the square, whatever. However you want to do it, and get the coordinates of the vertex, and so there you go. We'll work a bunch of examples so you can get a feel for this in the next video. Okay, now the last thing they talk about here is regression. So we talked about this when it came to the linear functions, and the idea is you've got some data points that you put into a scatter plot, and you look at that plot and you say, okay, this looks like it closely follows the shape of a parabola, right? So I would say that these points here, this relation here, this is between population of bacteria and time, that this is a parabolic relation between these variables. So I want to come up with the curve fit, the parabola that, whatever the parabola formula is, that most closely follows these data points. That's what's called regression. That process is called regression. And in this case, it would be a nonlinear regression. We looked at linear regression with the linear function. Here it would be parabolic regression. Now, I mentioned, though, just note, we could do linear regression here. And that would, the line that closely fits these points would be something like that. And the most common method of regression is least squares. We would find the equation of the line to where the sum of the squared distances, the sum of the squares of all of these distances of these points between the line is minimized. That's least squares. And you would do the same thing with a nonlinear least squares. You'd find the parabola, the equation of the parabola, where the sum of the distances between the points in the parabolic curve, the sum of the square distances, is minimum. But there's other methods of regression than least squares. But just like I mentioned when it came to the linear regression, we're going to come back to regression at the end of the course. We're going to look at regression as a whole in the end of the course, and we actually look at regression. This is something we really look at in a lot of detail in statistics. Okay, let's work some example problems.